Okay, so yes, I could not resist the title to split or not to split. That is a question. It was too funny. So I spent some time thinking about what I wanted to talk about to such a diverse audience. And so this is going to be different from my the last time I talked in a conference at Harvard, which was much more about the probability or mathematical side of my work and links more to the dependent data. So today I'm going to talk more about data splitting, and at the end I'm going to quickly talk about data augmentation in deep learning and trying to build some theory for it. Okay, so what do I mean by, let me just try to find a way to fix this to my close, because otherwise it's going to be cumbersome. Okay, can you still hear me? Okay, good. This is much better. Okay, so what do I mean by data splitting? I mean, many machine learning and statistical estimators, as part of their training, will at some point take the data and split it into 2 or more folds and then treat each one of those folds differently. And so cross-validation is, of course, a classical and important example of this. In cross-validation, we split our data into k different folds and then use this to try to estimate the risk of an estimator. Cross-fitting is, for example, in double debiased machine learning is another classical example of this. So many algorithms will train different estimators on different part of the data, and so we'll use some type of data splitting. However, despite the importance of data splitting methods in statistics and machine learning, our theoretical understanding of those methods is still quite lacking. And so today we're going to see 2 small pictures of this. We're going to talk about cross-validation and cross-fitting in causal inference, and we're going to try to gain some theoretical understanding for certain type of behaviors. And we're going to see that by doing this, we can discover some new behaviors and some surprising behaviors. And at the end, I'm just going to quickly mention something more linked to machine learning. Okay, so the first part of this talk is going to be based on joint work with Wenda Su, who is now, since 2 weeks ago, a senior researcher at OpenAI. So I'm very excited for him. And this is in the Annals of Institut.ai. So before we start, let's just set up the scene. So we're going to talk about probably one of the most used and useful methods in statistics, the cross-validation method. So to make things formal, I'm going to take a xi to be a sequence of ID random variables drawn from a certain distribution mu. And our goal is to estimate a certain feature theta of a distribution. So for example, maybe you want to estimate the mean, or maybe you want to estimate the median, or any other type of feature. But for simplicity, let's zoom on onto those 2 very simple examples just for the next 2 slides to fix matters. So to estimate this quantity, you're going to build an estimator, which is nothing else than a function of your training data exponential xn. So for example, in the first case, a natural choice could be the empirical average. In the second case, a natural choice could be the empirical median. To evaluate how good your estimator is and how useful it is, for example, for prediction, you're going to evaluate this by choosing a loss function L. In the first case, a natural choice is a square error. In the second case, a natural choice is the absolute error. One of the most important quantities that you might want to know about your estimator is the risk, which is the expected loss on a new independently drawn observation. Now, obviously, as you don't know what the distribution of your data is, you don't know how to compute this expectation, so you don't know what the risk is, and you instead need to estimate it. And you need to estimate it using data. So how can you do that? Well, the first naive idea that we all had before we studied anything was to propose as an estimate of the risk the following estimator. So we train our estimator, and then we would look at the loss over our training data, and we would take the average, and we call this the in-sample estimate of the risk. Part of this natural idea is that this will tend to systematically underestimate the risk of your estimator. It will be systematically too optimistic. You will systematically underestimate the risk of your estimator. So what's the next idea? The next idea is instead to split your data into 2. And on the first, let's say, M observation, you're going to train an estimator. And we're going to call this first M estimation your training set. And then on the remaining N minus M observation, on your holdout set, you're going to compute the empirical average of the losses over this holdout set. And this will give you the split risk. So the advantage of this idea is that here you're not using the same data for training your estimator and for evaluating its performance. The problem, obviously, is that there is always some part of the data that is left unused for learning. And this can be especially frustrating, for example, for high-dimensional estimators. So what is the next idea? The next idea is to split your data set instead into k different folds. Then iteratively, you take one fold out, let's say the first one, and then you evaluate an estimator on all the remaining folds, let's say folds 2 to k. And then you're going to evaluate the performance of this estimator on the fold you just took out. Here, the first one. You put your fold back, you took the second fold out, you do the same thing, etc., etc. This gives you k different estimators of the risk, and your k for quasi-dated risk is nothing else than the empirical average of those k estimates of the risk. And this is how you build a k for quasi-dated risk, and this is obviously one of the most used quantity in statistics. Please note that I'm going to keep on saying k for quasi-dated risk in the rest of my talk. I do not mean that k needs to be fixed. K's are allowed to go arbitrarily fast with n. A special case is when k is equal to n, in which case our folds contain exactly one observation, and we're talking about Leibniz quasi-validation. So it is k for quasi-validation is obviously extremely used, but it is obviously computationally much more cumbersome to do than the simpler split risk. I am, after all, computing k different estimators. And if my estimators are, for example, high dimensional, this can represent a significant computational burden. So natural question is it worth it? Or in other words, what is the statistical gain of doing k for quasi-validation compared to doing the simplest split risk? Another important question is, should I do two-fold quasi-validation? Should I do Leibniz quasi-validation? How should I choose my number of folds k? There is an old heuristic that maybe you should do square root of n for quasi-validation, but there's not a lot of theoretical understanding on this. So is there a statistically optimal choice of a number of folds, at least if you don't take into account computational questions? And last but not least, can we actually know how well we approximate the risk? So can we draw confidence intervals about the k for quasi-dated risk? So in the first, let's say 20 minutes of this talk, we're just going to answer those 3 questions. Is there any question about the setup? No? Okay, good. So as cross-validation is obviously a very studied question, there were a series of previous work that had studied those questions, and the most related to us are the series of work here that bounded the expected square difference between the k for quasi-dated risk and the notion of risk. And they did that under certain stability conditions. Now, they were not able to answer the 3 questions that I just raised. Why not? What made the analysis more complex? Presented the hurdle to the analysis? What presented the hurdle to the analysis is the dependence between the folds. The fact that I'm using each observation both to train an estimator and then to evaluate the performance of k-1 other estimators. To see this more clearly, imagine you're doing Leibniz quasi-validation. So I'm going to denote like this. You're training data exponentially xn, where you take out the IF observation. So the Leibniz quasi-dated risk can be rewritten as this empirical. Yes? Oh, you had a question? No, oh, sorry. As this empirical average of the loss over the observation xi for an estimator that is trained on everything but xi. So you could look at this and tell me, well, Morgane, this is an empirical average. Surely it's quite easy to study its properties. However, while it is an empirical average, it's an empirical average of highly dependent observation. For example, the loss on x1 is dependent on the losses on all the other observations because all the other estimators are trained using x1. And so this will introduce some dependence, and we'll see that this dependence is key to understanding the behavior of cross-validation. So still, we were able to determine what the asymptotic behavior of a k for quasi-dated risk it was, and so that allows us to exactly determine and study its rate of convergence. So what can I tell you? I can tell you that under general condition, the k for quasi-dated risk converge at the speed of 1 divided by square root of n is asymptotically normal, and I know what the asymptotic variance is. Please note that this holds no matter what is my choice of a number of folds. So this holds for two-fold quasi-validation as well as for Leibniz quasi-validation. Now, if a number of folds don't go too fast, so if kn is a little O of n, then the split risk is also asymptotically normal, but instead converges at the slow rate of a square root of n divided by kn. And I also know what the asymptotic variance is. You don't need to look and stare too much at what the asymptotic variance turns out. We're going to talk about this. But the key thing here is to notice that there is a term rho that is present in the asymptotic variance of a k-fold quasi-dated risk that is absent in the split risk. And this will determine what is the advantage of doing quasi-validation compared to the split risk. So before we talk more, let's try to gain some intuition. And for this, let's go back to what was hoped to be true. what was hoped to be true is that if I'm doing, my number of folds don't go too fast. Let's say I'm doing two-fold consolidation, and I have a very simple parametric estimator. It was hoped that as I get more and more data, those folds become more and more independent, and so the variance of a k-fold consolidated risk would be k times variance, smaller than the variance of a split risk. And that was seen as the best case scenario, the best we can hope for, and was referred to as full speed up. Doing k-fold consolidation would be like doing the split risk on k times more data. So now I have a question for you guys. Imagine I'm doing, let's say, two-fold consolidation on, let's say, parametric ridge regression. Do you think we are in the setup of full speed up? Do you think that doing two-fold consolidation is like having 2 times more data to do the ridge regression? I'm patient. Yes, no, maybe. Hallelujah. Thank you, Yanai. Was that an educated guess based on the way the question was asked? Or on you?
I don't think it was an educated guess.
Okay. I had hoped that if the answer was yes, and you're going to see that actually things are a bit more surprising than this. Okay, so now that we know exactly the asymptotic distribution of a k-fold consolidated risk, and we know exactly the asymptotic distribution of a split risk, we can exactly compare the speed of convergence. And so we see here that determining what this term rho is key to determining what the speed up is. If rho is equal to 0, then good news, the world is beautiful. We're in the setup of full speed up. Doing k-fold consolidation is like having k times more data to do the split risk. If, however, rho is positive, that means the dependence between the fold is hurting you, and doing k-fold consolidation is not as helpful as you would hope for it to be, and you're in the setup of less than full speed up. If, however, by some miracle, rho is actually negative, that means that the dependence between the fold, far from hurting you, actually help you, and that the k-fold consolidated risk is converging even faster than if you had k times more data to do a split risk. And we are going to see that this happens even for very simple estimators. Okay, so before I move to showing that all of those different behaviors, let me just make a few remarks. The first one is we also provide, please note that we provide an estimator for the asymptotic variance of a k-fold consolidated risk, which means that the first time someone can actually draw confidence intervals. And we also obtain Berry-Esseen bounds, which allow you to know how good your asymptotic confidence intervals are in finite sample. Most surprisingly, note the following fact, that the asymptotic variance of a k-fold consolidated risk does not depend on your choice for the number of folds. So you have the asymptotic variance is the same for two-fold consolidation as well as for leave-one-out consolidation, which was at least surprising to us. But obviously, the bias depends on the number of folds. As the number of folds increases, the size of my holdout sets is going to decrease, and so my bias are going to improve. And so that means that for most statistical estimators, the optimal choice of the number of folds is to choose k to be equal to n and to do leave-one-out consolidation. At least statistically speaking, if you don't take into account any computational questions. Okay, so let's try to understand this behavior of the speed up of consolidation. And to do so, we're going to zoom on a class of estimators that are quite simple, but while they're quite simple, are very important for statistics. And the point of them being simple is to show that even for very simple parametric estimators, we already have a rich sets of behavior. So this is not a feature, for example, of having a high-dimensional estimator. So those are going to be parametric M estimators. So they're going to be trained in the following way. I'm going to have psi. I'm going to choose psi to be a training loss. And then I'm going to choose my estimator to be the one that minimizes my training loss as measured by psi. And then once I have trained my estimator, I'm going to evaluate this performance using a potentially different loss L, testing loss L. If I'm training and testing with the same loss, so if psi is equal to L, then good news, I am in the setup of full speed up, rho is equal to 0, the world is beautiful, doing k-fold consolidation is like having k times more data to do the split risk. This is, however, not the case if you train your estimator with a surrogate loss. So for example, let's look at the case of parametric ridge regression. So here we are training our estimator with a square loss penalized, and we're evaluating it with a square loss. In this setting, very surprisingly, rho is actually negative. So Yanai was right. Doing K-fold cross-validation here is like having more than K times more data to do the split risk. So for example, imagine you're doing two-fold cross-validation, I'm plotting here the ratios between the variance of the K-fold cross-validated risk and the split risk. You can see that doing two-fold cross-validation for which regression is like having more than 3 times more data to do the split risk. And this is very surprising for me. I was not expecting to see this, especially for such a simple estimator. And more surprisingly, even, someone has a raised hand. Should I look at it? Or should I? Maybe I will take online questions at the end of the talk, because I think it would be too disturbing, yes. So very surprisingly, what the speed up is, Rho can be actually negative even for very simple estimators. And so doing K-fold cross-validation can be like having more than K times more data to study the split risk, even for very simple estimators. More surprisingly, it does not only depend on your estimator and how it's trained, it depends also on your distribution. And so here we're going to see a very, very simple example. Imagine I flip a coin. When my score falls on head, I'm generating my distribution according to a certain distribution D1. When it falls on tail, I'm generating it according to another distribution D2. So I'm generating my data x1 until xn like this. And then my goal is to try to classify them. And so for this, I'm using a very simple linear discriminant analysis, and I'm evaluating all of this using the 0-1 loss. Then what can I say? If I choose D1 to be a gamma with parameter 10, 0, 15, and D2 to be a gamma with parameter 1, 1, then Rho will be negative. And doing K-fold cross-validation and doing two-fold cross-validation is like having less than 2 times more data to do a split risk. The dependence between the fold is hurting you, and the K-fold cross-validated risk is not converging as fast as we would hope for it to be. But if you simply change the distribution D1 to be a gamma with parameter 110, or 1, 1, no, 110, sorry, suddenly Rho becomes negative. The dependence between the fold is helping you, and doing two-fold cross-validation is like having more than 2 times more data to do the split risk. And so this was a very surprising behavior to us. So what do we see? We see that the behavior of cross-validation is much more complex than previously thought. It's even for very simple estimators, even when you have the number of folds is not large. Also note here that the ratio of speed up does not change no matter what is your choice for the number of folds. So it will be the same for two-fold cross-validation than for square root of n cross-validation. And so this kind of illustrates that we did not really understand, we still don't really understand the behavior of cross-validation, but gaining some understanding to it can reveal some very, very surprising behavior. So let's try to understand what is happening here. Well, we said that the key term to determining what the speed up is this term Rho that is introduced by the dependence, that is introduced by the fact that I'm using the same observation both to train an estimator and then to evaluate the performance of yet another estimator. And so if typical observations that are hard of your learning algorithm, so on which you suffer an important loss, are, quote, not bad learning example, but are a helpful learning example, then Rho would tend to be negative. So this, for example, is what happens with the parametric ridge estimation framework. So learning example on which you suffer an important square loss will help to, counterbalance the penalization and will be important learning examples. And so in that case, doing K-fold cross-validation is more helpful than we would hope for it to be. We're in the setup where Rho is negative and the world is beautiful. If, however, observation on which I tend to suffer an important loss are bad learning examples, for example, the outliers, and Rho would tend to be positive. Okay, so so this gives us a first picture into understanding the behavior of data splitting algorithms. I'm going to go to the second part, but before that, I wanted to know if there's any questions. Okay. So the second part of this talk is based on joint work with Jane Chen and Vasilis. Vasilis is a professor at Stanford, an assistant professor at Stanford, and Jane is a PhD student in our department. And in this part of the talk, we are going to try to talk about we're going to talk about debiased machine learning and the role of data splitting in debiased machine learning. Just to fix the setting, I'm going to take Z1 into Zn, once again, to be a sequence of ID when available, drawn from a certain distribution mu. And our goal here is going to be to try to estimate a certain parametric feature, theta, zero of your distribution. And this parametric feature here is characterized by the fact that it is a solution to a certain equation. Now, the difficulty is that this equation also depends on some unknown nuisance parameter that might be high dimensional or even infinitely dimensional. So, and we want to use the fact that theta zero is a solution to this equation to inform our choice of estimator. So what is this equation? So I have this function m that takes as input our data points and our parameters. And it's such that when I take the expectation with respect to the data point and evaluate it at the true values of the estimators, this expectation is equal to 0. So this is a solution, the equation to which theta 0 is a solution of. We are going to call this expectation a moment, and we are going to call this function m a moment function. And our goal here is to estimate theta 0. So many problems, and this is called the generalized method of moment, and many problems fall into this framework, notably in semi-parametric inference or in causal inference. So to see this, let's look at this quick example. So here for partial linear treatment effect. So imagine you have some type of outcome, for example, your quantity of antibodies in your blood, and that depends linearly on your treatment. For example, did you get a COVID vaccine or not? But it also depends on some unknown function of your past medical history, for example, your BMI, your age, and things like that. Your goal is to try to estimate the treatment effect, and so to try to estimate theta 0. The key point is that this fits into this framework of the generalized method of moment, because there is a function m. You don't need too much to worry about what it is right now, such that the corresponding moment, capital M, character is such that the such that theta 0 is a solution to this equation. And so you can see this too through the lens of the generalized method moments. So now that hopefully I'm motivated to you that this is an important problem to study, how would you estimate theta 0? Well, the most natural way to estimate theta 0 is to do the following. So you are going to first choose your favorite statistical or machine learning method, and you're going to use it to estimate your nuisance parameter. And then once you estimated your nuisance parameter, you're going to plug it into the moment function here. And you're going to propose as an estimator for your target parameter the solution to this empirical equation. And this is kind of natural. The true parameter is the solution to the equation. So we're going to take our estimator to be the solution to this empirical equation. Now, if you remember, theta 0 is a parametric estimator. So we would like to be able to derive it at the parametric rate of 1 divided by square root of n. The problem here is that how well we can estimate theta 0 depends on how well we can estimate the nuisance parameter. And because the nuisance parameter can be high dimensional or infinitely dimensional, in general, we cannot estimate it at the parametric rate, but at a slower rate than 1 over square root of n. Also, maybe we want to use some type of regularization, and this regularization is going to introduce some small bias that means that in general, when you combine those two facts, we cannot guarantee to be able to estimate target parameter at the parametric rate, but only at a slower rate. And the asymptotic distribution is not necessarily asymptotically normal, which means that it's more complicated to draw confidence intervals. So is it the end? No, not if you use something called Niemann orthogonal moments. So those are very famous moments because they satisfy the following additional property. They are such that when I evaluate my moment, and I introduce some small perturbation on my nuisance parameter, this doesn't have any first order effect on the value of my moment, in the sense that this derivative here is equal to 0. And so that means that I am less sensitive to mistakes that I might make in estimating my nuisance parameter. I'm only sensitive to the second order to the mistake that I may make in estimating my nuisance parameter. And so hopefully this would mean that even though I can't estimate my nuisance parameter at the parametric rate, because I'm less sensitive to mistakes I might make about it, it might still mean that I'm able to estimate the quantity that I do care about, the target parameter, at the parametric rate. And this is indeed the case, and this was at the birth of a lot of interest, and there's now a huge literature around debiased machine learning, how to build Niemann orthogonal moments and things like that. And this is all coming from the fact that we have the following guarantees. This is what we can tell. If your nuisance estimator belongs to some type of low complexity class, for example, is Donkster, and you can estimate your nuisance parameter not at the parametric rate, but at the slower rate of little o of n power minus 1/4, then under certain general condition, we can tell you that theta hat is still asymptotically normal and still converges at the parametric weight. And so the world is beautiful. Even though we had to deal with this nuisance parameter, we're still in the beautiful world of parametric inference. The problem with this is that many algorithms that we would like to use to try to estimate the nuisance parameter do not fall into this class of this low complexity class. And so the theory does not extend. So to try to resolve this problem, there was this beautiful paper that proposed to do instead to use data splitting. So here is what they propose to do. You're going to split your data set into two parts. And on the first, let's say, M observation, you're going to estimate your nuisance parameter. And then you are going to, and the remaining N minus M observation, you're going to estimate your target parameter. And you're going to do it in the same intuitive way. You're going to take your estimate of a parametric, of a nuisance parameter, you're going to plug it into a moment function, and you're going to propose your target parameter to be the one that is a solution to this equation. And the advantage of this is that you're training your data into a different part, your nuisance parameter on a different part of the data that you're training your target parameter. And so this means that in general, as long as you can still estimate your nuisance parameter at the slow rate of a little o of n power minus 1/4, we still can obtain, we can still estimate our target parameter at the parametric weight of 1/square root of n. And this led to a lot of experiment, and this is a very nice guarantee. The problem with this is that splitting your data into two is kind of data inefficient. You're wasting some data, especially you would like to be able to train your nuisance parameter that might be high dimensional or infinitely dimensional on your entire data set. And so the natural question you might ask is, do we really have to split our data into two? Or in other words, can we still guarantee that we have all the nice theoretical guarantees we want to have about learning our target parameter without having to require data splitting? And the answer is yes, as long as you assume some type of stability conditions. So there was some previous work that has studied exactly these questions, and instead of assuming that you can, but they required some stronger condition on how fast you can estimate the nuisance parameter. And so we're going to be able to go around those conditions by assuming instead some stability property. Okay, so I'm presenting this just here in the simplest setting of linear moments. In the paper, we do it for much more general moments. This is just for illustration. Okay, so imagine that my moment takes this nice form here, and so notably it's linear in theta, and it's multiplied by the function a. I'm going to need the following condition. I'm going to need that I can estimate my nuisance parameter still at the slow rate of a little o of n power 1/4. I still require that my moments are an event of orthogonal. Then I'm going to need to require the following stability condition. I'm going to require that if you take your training data, Z1 into Zn, you take out the F observation and you swap it up by an independent copy, then that doesn't change too much the value of your nuisance parameter, or your estimate of a nuisance parameter, in the sense that this difference here is a little OP of 1/square root of n. And we require a similar condition on the other function u. So as long as basically this is kind of an algorithmic stability condition, as long as changing one of the training example does not change too much the value of my estimators, then I will say that those conditions are satisfied. Note that many estimators do satisfy those conditions, including some high-dimensional estimators. So as long as those conditions hold, what can we tell you? Doing data splitting is not necessary. You will still, without data splitting, you will still converge at the speed of 1/square root of n. You will still be asymptotically normal, and you still have the same asymptotic variance when if an oracle came and gave you a true value for the nuisance parameter. And so here we can see that maybe doing data splitting is actually not necessary as long as you have these stability conditions. Note that these composed stability conditions are actually tight. We can give you example at which the difference is not a little o, but exactly on the order of 1/square root of n, and for which the asymptotic distribution can become completely arbitrary. It can be asymptotic Poisson, exponential, or not fall into any of the universal class. So hopefully by those two examples I showed you that there's a need now to try to understand better the behavior of algorithm that use data splitting. And then when you do that, you might gain some very valuable insight. For those who didn't care too much about data splitting and classical statistics, because this was very classical statistics, I just wanted to mention something else that I'm a bit excited about that is linked to, that is still linked to data splitting, or at least sample reuse. After all, cross-validation is a method in which I'm using my data points in many different ways, both to train estimators and to evaluate different estimators. And so this is more linked to data augmentation. So this is a paper that is in revision at GSSB, and there will be a new version with what I'm going to show you very soon. This is done with an amazing PhD student whose name is Kevin Hong, who is a PhD student at GSSB at the University of College London, and Peter Owens. So here, by data augmentation, I do not mean the MCMC classical statistics data augmentation. I mean data augmentation more in the machine learning sense. So what is data augmentation? Data augmentation is a classical framework in which in deep learning, where you take your data that you have and you artificially transform it. You artificially create new example of data by slightly transforming your data. So for example, imagine your data set is a data set of pictures of animals. And for example, here of cats. You can slightly translate your pictures of cats. You can slightly rotate them. You can change the contrast. You can add noise. You can add any of those like random transformations. And then, so once you have augmented your data set, then you can still train do your machine learning pipeline and try to estimate or classify or build your classifier. And data augmentation has shown to have great empirical success in deep learning. Now, there's not really a theoretical understanding for why. When is data augmentation helpful? When does it hurt? Why is it helpful? But it is something that people have observed often to be useful. And there's two heuristics for that, at least that I'm aware of. The first one is that there's a lot of symmetries in nature. A picture of a cat is a picture of a cat, even if I flip it on its head. And so that by including some perturbed example of data, that will force my machine learning algorithm to learn this invariance, this symmetry, and it will help us choose a better estimator. And this was, sorry, I take naps and I don't turn off my alarm clock, and I drive not only my partner insane, because at 1:43 for 4 months, my alarm clock rang every day at 1:43, and I keep on forgetting to turn it off. So sorry about that. Oopsie. So actually this is fast. Okay. So I spoke faster than I thought I did. Okay. It's okay. So I forgot what I was going to say. Yeah, so this has been studied notably in many different empirical studies, and has shown that data augmentation sometimes help and sometimes hurt actually to choose some type of invariant network. And the second heuristic way it might help is that more data shouldn't hurt. Having more data might help your statistical learning, especially if your augmented data has the same distribution than your original data. And this is more the second heuristic that we were kind of interested in studying. And so we were trying to understand what is the effect of data augmentation on the statistical learning of our estimators. So I'm going to make a disclaimer. I'm not saying anything about deep neural network, but what I'm going to say holds both in the under-parameterized regime and the over-parameterized regime. For example, for high-dimensional regression, and everything would carry through also for two-layer neural network, but I don't know if that was that interesting. Okay, so what do we mean by more data shouldn't hurt? Here's what we would hope to see. Imagine that I'm looking at, for example, the confidence region of my estimator. I would hope that when I do data augmentation, my confidence region is smaller than when I don't do data augmentation. And this indeed can happen, and notably it was shown by some previous paper that this does happen in very simple parametric M estimator case under certain stability symmetry conditions. But as soon as you step out of this nice world, a lot of more complicated behavior can happen. And so we wanted to kind of understand the impact of data augmentation on statistical learning. And so here is what we can tell you. Under certain type of stability condition, we show this kind of universality result that the behavior of your augmented estimator, or your estimator trained on your augmented data sets, is about the same as the behavior on of your estimator trained on some other distribution that we get to choose. It's not always going to be a normal, but this is a distribution that we can choose. I thought I was going to have only 10 minutes, so this is very high level, but this is what we can show. And so because we get to choose this observation and we show this universality, we can then study and exactly characterize the asymptotic behavior of many estimators, both when they're trained with and without data splitting. And we can do this both in the over-parameterized and under-parameterized regime. And so we can notably try to understand what is the effect of data augmentation. And so here is, in 5 minutes, what we can observe. So first of all, when your estimator is very simple, let's say you're looking at an empirical average, then data augmentation will always help. If you're looking at a simple parametric M estimator and the distribution of your augmented data is the same as your original data, so for example, your data was invariant under rotation, then the distribution of your data was invariant under rotation, then you can easily prove that data augmentation will always help. But as soon as you kind of step out of this nice world, things get more complicated. And rather than give you a full theory, I'm going to just show you 2 examples quickly. One is for in the simple ridge regression setting. So here this is in the regression setting. I have y equal x beta plus epsilon. I don't know what beta is, and my goal is to try to estimate beta. The dimension here in this first example is assumed to be much smaller than n. It can grow as a small power of n, but it has to be much smaller than n. So here we are in the under-parameterized regime. In this under-parameterized regime, we can exactly characterize what's the effect of data augmentation on the risk and on the variance of our data, or of our estimators. And then we observe a certain number of surprising behaviors. So the first one is the effect of data augmentation on the variance of your risk will depend on the correlation between your original data and your augmented data. Yes? So I'm just transforming x and sometimes y at the same time. So for example, you can, on top of transformation, you can add noise. That's one we will see. So you just add noise. You can rotate and multiply things. You can do cropping. You can do, does that make sense? So your data is x and y, and then you transform your data x and y in different ways, yes. In the second case, in for double descent, we're going to see is we'll be adding noise. In the first part of the simple setting, the example I'm going to show you are for cropping and rotations. So you take your x, you slightly rotate it, and you can. Yes, exactly. Yes, yes. So you will. There will be a correlation between your different augmented examples, especially, for example, imagine you slightly rotate them randomly, there will be a small correlation. And what we can see is that the variance of the risk will depend on this correlation. So intuitively, the less correlated they are, the more independent, they're not independent, right? The more dissimilar they are and the more dependent correlated they are, you know. And so here we are plotting indeed some simulation, and this is backed by the theory of how this is the correlation between your augmented data and your original data, and this is the variance of your risk. And you can see that at the beginning, when you augment the correlation, it hurts the variance, and then at some point, it actually starts helping the variance. So the behavior of data augmentation here is a bit complex. Let's look at this other simulation here. So here we study the data augmentation is random cropping and random rotation. In the first row here, I am, this is looking at the variance of my estimators. And here I'm looking at the variance of the risk. And so you can see here that for random cropping, data augmentation helps both reduce the variance of your estimator and the variance of your risk. However, for random rotations, which by the way, in this setting, we are distributionally invariant, so the bias is 0, you are both helping, data augmentation helps to reduce the variance of your estimator, but it actually hurts the variance of your risk. The variance of your risk is now significantly high. And so we can see once again that here the behavior of data augmentation is much more complex. And we have like very clean theoretical understanding of this. I just wanted to kind of show you and that the behavior of data augmentation is much more complex than we thought, and some kind of nice illustration of that. So here, this is when the dimension is moderately high. what happens in high dimension? So in high dimension, I'm going to study this through looking at the effect of data augmentation on the learning curve. So the classical learning picture that we all know of and that we all loved was the following, which as I get more and more data, as I increase the complexity of my model, at the beginning, this helps my learning. And after a while, when I increase my size of my model too much, I risk overfitting, and my risk will once again start to increase. Right? This is the classical U-shape of learning. Now, in the last few years, it was noticed, notably by some people here at Harvard, that in many machine learning settings, this is not the case, right? And what was started to be pointed out is that there seems to be more double descent curve type of phenomenon, which is that at the beginning, as we increase the complexity of our model, the risk of our estimator will at some point once again increase as I enter the overfitting regime. But if I keep increasing it, then at some point it will decrease again. And this was noticed by many people, and many people here were to be at Harvard. Notably, this paper looked at this and observed that this also holds for many deep neural network architecture. And so the effect of double descent is not really understood for deep learning, but it is something that has been very intriguing and very well studied and has generated a lot of excitement. However, it's completely understood or it's well understood in the much more simpler setting of high dimensional linear statistics, because in that world, we can rely on some random matrix theory to help us with that. And so in the setting of high dimensional regression, we understand and we also observe the double descent curve. And so what you can ask is, what is the effect of doing data augmentation on the double descent curve? And so this is, and so we also can show that the following. So imagine that you're doing once again linear regression, and here your data augmentation is you're going to inject some noise. And here each observation led to 5 augmented observations. So I add 5 times some independent noise. And so here is what we can observe on the learning curve. For the augmented estimator, once the data, the dimension reaches the same dimension as soon as the dimension reaches the size of my sample size, then will be a spike. And then after a while, the learning curve improves, and there's a bit more complex things here. When you look at the estimator trained with data augmentation, what you can observe is that there is still a small spike at the interpolation threshold. So when the number of data points is the same as the number of parameters. But there's a second, but the spike is much smaller. And there's a second spike here at phi. And remember, we augmented our estimators by creating 5 new augmented examples. All of this, we have some theory, and this will be very soon on arXiv. We had this is in the revised paper, which is much more exciting than the older paper. So we are very thankful to the reviewers who forced us to do this, because things turned out to be pretty cool. And so here we can see once again that trying to understand the behavior of estimators, that you have data splitting, or that you're instead using your samples many different ways, can lead to great theoretical insight. And I think it's very interesting. And I think this is an invitation to people to join. I just wanted to just quickly mention that. So this is one side of my work. Some of you know me more for my probability work. And this was not kind of fitting into this talk, but I just wanted to put this out for people who might be interested to chat with me, because I'm kind of excited about this. I've been interested with Lasamaki at Microsoft in trying to propose new ways to build concentration inequalities. And the aim for this is for our concentration inequalities to be smaller, and notably to become tighter and tighter as we get more data. And the motivation for us is coming from data-driven decision-making problems and reinforcement learning, where concentration inequalities are used over and over again to kind of quantify the uncertainty that we have. And because they're used over and over again, we want to get as tight confidence intervals as possible. And Bernstein and Azuma and all the concentration inequalities we know of are actually extremely loose. They are the correct weight, but the constants are extremely bad. And notably, they do not improve as we get more and more data. And so we propose some new ideas using optimal transport to try to get some new concentration inequalities. So if you're curious, please reach out to me at the end. Okay.